Well, looks like it's official. Welcome back, everyone. Any questions at all to start us out today? Okay, well, welcome to midterm week. That means at the end of this week, you're halfway done with the semester. That's definitely worthy of congratulations. I mentioned before, there's no special midterm project or assignment or anything like that. In fact, I forgot to write a quiz on this week right here, so we don't even have a quiz 6. All we'll be doing the midterm week is just reporting your grades as they stand on Friday of this week. So if you go up here where your grades are, we'll just see something new duplicated from your course grade called midterm grade, and that is literally your midterms at the end of this Friday. Aside from that, I don't have too many other announcements. Aside from, let's see here, we're mostly done with section 3.4. We're on the third example, and we have our upcoming exam. It's still a ways out, but I'm going to be posting information pretty shortly on this. By the weekend, you should start seeing documents like the actual notes provided on exam 2, as well as some review topics and the coverage. Well, any questions at all, folks, before we jump back to the product quotient rule? Okay, well, here's where we left off. Right here, about to do another tangent line equation kind of problem. I duplicated this table down, so it just got copied and pasted below. And this is one of the tables I'm thinking about actually including on the real upcoming exam too. You'll have pretty much your major differentiation formulas from things like constant rule, constant multiple rule, all the way from the power rule, product rule, and quotient rule here. Well, let's give this a try just for the sake of warm up. This is kind of a nasty one to warm up on, but we'll make it happen. It says, find the equation of the tangent line to the graph y equals f of x, and here's how f of x is defined, at 0, 0. So anytime you see a tangent line equation kind of problem, you can always break this down to a sequence of steps. Really, the very first step you want to achieve is you just need the derivative. That's going to give you the slope to the tangent line. But we first generically calculate f prime right at x. For us, that's when the adventure begins, because we're looking at a quotient of functions. We need to use this quotient rule right above. So we can begin by going, you can think of your quotient rule in this format. That's good for memorization. Actually applying it, it might look more like this, where you see f prime, put a blank and a prime symbol on it. Here's for g. It'll be f times g prime. We'll put a prime symbol on that one. And for where you see g squared, we'll just put a blank and power 2. After that, we can start thinking of this as top function versus bottom function. Color coding is not required, but here's a great way to memorize this. If you like that structure there, all you put is x e to the x in these two positions. After I reformat this to make it fit a little bit better. Never seem to draw these out as large as they need. Okay, I think that fits slightly better. And then over here, x e to the x. Then for denominator, x squared plus 1 will go into all the remaining positions. So here it is here, here, and here. And then we're just about done. We just need to take care of this derivative, and put the value of 0 coming from the point, and we'll be well through steps 2 and 3. But that one's the nasty one. We started with quotient rule, and midway through quotient rule, this can happen. It can happen in WebAssigns, quizzes, maybe here and there in exams, but not as often. I try to make the exams a little bit easier to move through concept to concept, not one giant question. So think of example 3 as there's really like 2 good exam questions kind of baked into this one. This right here requires product rule. And so let's do the product rule simultaneously to the right here in the margin. We'll just move the participants windows ever so slightly. You're still there. So we have x e to the x prime. So we can break this down as derivative of the first function, copy the second, plus copy the first function and slightly more space. There we go. This should fit. Derivative of the second function. So some kind of breakdown, but this time I'm looking to this portion of the notes to write down the structure. I won't do color coding on this one just so it doesn't get too crazy. But here's the first factor. It goes into these positions. And here's the second factor, e to the x, going into all the other positions. That x looks a little bit weird. Let's fix that one. So here's the product rule so far. On this portion, we need to calculate x prime. That gives us a 1, multiplying e to the x. Then across we'll have plus x. And derivative of e to the x, always worth remembering and mentioning, is itself. So that one's done. It simplifies back down to e to the x plus x e to the x. Now let's carry this in yellow to show the substitution. All this stuff is just going to drop right back in there, and we'll walk through the rest of the quotient rule, finishing off that product rule. Any questions so far, folks, to this stage? Okay, still in step 1, we have to complete our derivative, and so here it finally is. You can scroll just a touch. For the portion in yellow, let me pull out a parenthesis. We have e to the x plus x e to the x. And that's how that substitution went down. I'll drop the color coding on these things that we're just copying. So x squared plus 1 minus x e to the x. And that derivative's not too bad. Derivative of x squared will turn into a 2x. And the plus 1 constant will vanish. So that whole derivative there is just a glorified 2x. Finally, everything is divided by x squared plus 1 to the power 2. Ordinarily, we'd probably simplify this a little bit here and there. We'd probably distribute these two parentheses, combine these, and start canceling like terms. But if your objective is just to get a tangent line, that means your next move is probably just to go over here and input in the first coordinate inside this derivative. Pointing to the 0 specifically, always think of it the very first coordinate. So if this was a 1, 5, 1 is going inside, not the 5. That takes us to step 2. And step 2, this is the reminder of the geometry of the derivative. At any x value, and here's 1 at 0, if you plug it into this formula, what it's actually telling you is the slope m to the tangent line we're trying to build. So m is f prime at 0. I'm going to use these red arrows as a form of color coding since they only help me to load 3 pens onto this. I think that'll save a little bit of time. So here's the derivative. Because it's f prime at 0, everywhere you see an x, you're just throwing in a 0. That's why there's less value in simplifying this one if you're just throwing in a 0 to wipe stuff out. In that position, you get e to the 0. E to a power 0 is a 1, so there's no cancellation there. But this is a 0 multiplying, so I'm just going to write plus 0. There's really a cancellation in that position. This will turn into a 0 plus 1 minus. All of this is 0 due to that x right there, so I'm just going to go minus 0. And down below, I'll just write this as 0 plus 1 squared. So lots of simplifications out of nowhere. Right here, that's a 1 surviving, so I have a 1 times a 1, essentially. The whole numerator is a 1. 1 squared is just a 1, so the whole denominator is a 1. And that's just a really weird way to write 1. So we've got it, folks. That's our slope to the tangent line. Watch out for the wording here. Sometimes on exams, if I decide I want to make it a little bit shorter, I might not say the equation of the tangent line. It might say just the slope of the tangent line, in which case you're done. So if you ever see just slope right here, you don't need the third step. The reason we do need the third step is it wants the full-on equation, y equals mx plus b for this tangent line. So here's the step 3. The way I think of step 3 is I usually put down here where you see the 0, 0, I think of it as an x1, y1, because I usually use this formula. Y minus y1 is slope m times x minus x1. The big superstar in this process is the slope m that we have right here. We found it's a value of 1. So we'll go y minus, look up y1, nothing special, it's a 0 here, equals a slope m. That one we look up and find it came to a value 1. Then back for x minus x1, this will be x minus 0 again. We're going through the motions even though we know it's 0, just for the pattern. You'd simplify all of this, but now it resolves to just y equals x. And that means we did it, folks. We probably have the equation of the tangent line. I would probably check it out by graphing the tangent line and the original function side by side like we've done in the past, make sure it all looks right. But these are the major steps you'd want to take for any kind of process that looks like that. You might have noticed that this was in sections like 2.9, 3.1, 3.2, 3.3, and in this section. So it's a pretty common question. Well, any questions at all, folks? Questions at all, folks, on getting through this process? Okay, this was the major one that we definitely needed to return to for the sake of the homework. The next one we're going to take a look at is really kind of a preview. It's stuff that we have to face when we're in chapter 4. For the moment, it's kind of nasty. So again, if it seems really weird, think of this as a preview. It's extra practice, so it's not a sudden shock when we get to chapter 4 and we're doing these kinds of problems out of nowhere. And it's a worthy application. It says here, the power that a battery supplies to an apparatus such as a laptop depends on the resistance of the battery. You don't want to expel all the power at once, I guess is the thought there. They tell us next, for a battery of voltage V, so V is indicated in this formula, internal resistance in ohms, that's lowercase r, it's represented here in the formula. The total power delivered to an apparatus of resistance uppercase r, so that one there, is given by that function. So we have two kinds of resistors. Let's see. Apparatus of resistance R is this one. That's the internal resistance of the battery. So I think the thought here. Now it says, assuming V, R are constant, calculate this derivative, dP dr. That right there, that denominator has indicated that uppercase R is the actual variable in this problem. Everything else is now considered a constant. So we'll calculate that derivative, then give a practical interpretation using the context. But it's truly a pretty difficult problem. The best way to tackle these is we want to think of it like this stuff. If it's X's and Y's, we know exactly what we're talking about, but that's where the conflict comes in. If we translate everything into X's and Y's or X's and f of X's, then we lose all the context here, and you have to translate the context back in to know what you've just calculated. It's for that reason that people in engineering sciences leave the variables exactly like that. But if you're learning this stuff, an analogy is great. So here's the analogy. Think of this function p as being written out this way. F of x equals, they said v and r are constants. So we can't do this on a real problem, but if we're trying to tackle on a hard one, we absolutely can. I'm going to put a constant there. Imagine it as a 5, so now it's 25. Uppercase R, we know is the variable because this was dP dr. That's like the dx at Leibniz. So just put that in as an x. Then down below, think of this as an x plus. Let's see, lowercase r, they said right over here is constant. Well, let's maybe think of it as an x plus 1 to the power of 2. So now if you can differentiate this function, you can differentiate this one, but you might have to look to the left and to the right to see how the analogies compare. But that's the best way to learn how to differentiate these things after dealing with f of x's for so long. Let's actually do it. Let's calculate the derivative on this one, and we'll come back to this one and show how to do it if this was all we were looking at. First thing you need over here is a quotient rule, so we'll set up this way. F prime of x equals, we'll take the derivative of the top, multiply it by the bottom copied in, so x plus 1 squared, subtract, copy the top, no change on that one, but then multiply it by the derivative of the bottom, and I think we're going to need a bracket for that one. No, parentheses should work. We're going to multiply by the derivative of the bottom, and one small complication is that one's not a nice derivative to take and calculate right away until we get the chain rule. That's the next section. But we do know how to handle x plus 1 squared. You just FOIL it out. That's x squared plus 2x plus 1. And I forgot my prime symbol there, so there it's copied in. That's what you're differentiating. X squared plus 2x plus 1. And there's no way that's going to fit, is it? Let me see what I can do here. I need to write a little bit smaller or move things further to the left. What are the two? 25x, x squared plus 2x plus 1. And here's the prime symbol. I think it just barely fit on the corner. Is that readable to everyone so far? Okay, try not to jam them in too close going forward. Then down below, it's going to be x plus 1 squared, but that whole denominator is still squared, so it's squared squared. We'll raise it to the power 4, multiplying those exponents next. So this is how we would start it. Now we're taking derivatives as normal. The derivative of 25x is 25, multiplying x plus 1 squared. On this one, we'll copy a negative 25, but then the derivative on this one will turn it into a 2x plus 2. Next, the denominator becomes x plus 1 to the power of 4 altogether. We would do more steps to simplify it, but as far as the analogy goes, this is where the calculus will end. And so let's go back over here and try it on the larger one. First, any questions, folks, on doing the quotient rule normally this way? Okay, now let's do this for that function. Now, whenever you're differentiating stuff and there's too many symbols, you always want to know what are the constants. That has to be supplied some way, somehow, some way. But here they're just saying verbatim, V and R are constant. Next, the major reminder is from dr right there, the variables are in that location. And here's the value of Leibniz notation. When it says dp, dr, that is what Leibniz notation is trying to indicate. Sometimes there's a lot going on in your function, and sometimes there could be multiple variables, non-constant. But this one always tells you what you're differentiating for. It gives you the exact instructions, in other words. So going back, this one's a pretty tricky quotient rule. So another good strategy is, let's work this one carefully by using the placeholder strategy. And there it is. So that gets us set up. Next, copy in the numerator into the first positions. So it'll go here. And here. Last, the denominator goes into all remaining positions. So it'll be r plus r, and I'll write out squared on this one where that placeholder symbol was. Seemed like the fastest way to write it in. When I put this one in right here, again, there's an extra complication where if you're differentiating that, as it stands, we probably want to FOIL it first. This FOILs as uppercase r squared. Let me give a little more space on this one. Plus 2 little r uppercase r. Plus, should just left that one open, r squared. Still has a prime since we still need to differentiate it. Okay, so now finally, the last thing is we'll throw that into the denominator, r plus r squared. I left this one completely in black since we're not differentiating. We're less worried about what the variable is. Okay, so far this is our setup. It's pretty much what we wrote here. Only difference is it was very clear what varies and what was constant over here on the right. Over here, it's less clear. The objective is you have to train your eyes to see every symbol that's not R as a literal constant as you differentiate. So in fact, when you go to differentiate this one, what did we do? Think of this as a 5 or a 25. This is a to a power 1, so R vanishes when we take that derivative. And that's what we did over here. Derivative of 25x becomes 25. This is much like the same thing. It just becomes the constant itself copying in. That is pretty tricky, though. Does that make sense to folks so far? Okay, So in other words, think of this right here and right here as well as the 25 here and here in the process we did in the analogy to the right. We're thinking of anything that's in black as opposed to blue as a literal constant. Over here, nothing special happens. We'll just copy in r plus r squared. Again, nothing major on this one if there is no derivative, so no complication. So I'll draw parentheses and just write minus v squared r. But this one we do have to be a little bit careful of. Honestly, I think the first one is more confusing than the last derivative just because of the v squared. If you're differentiating this, you would probably go 2r. This one's now pretty tricky. 2 little case r, uppercase r. But we did this one right here, where it said 2x. If you differentiate something like that, all you get is the constant 2. The constant on this one is not 2, it's 2r. So if you differentiate this thing, you get a constant of plus 2r. And let me circle that one in red as well, just to tie together the analogy to the right. Finally, the whole denominator would be r plus lowercase r power 4. We did it, folks. That's finally the full derivative on this one. It's a quotient rule in an applied setting with non-standard variables. This absolutely takes practice. Any questions or comments with getting to that stage? Okay, well, let's now see what else we have here. It said calculate dPdr. Then give a practical interpretation using the context of this problem. If this was an actual example problem, not a preview problem, we'd probably also simplify it a little bit more. In fact, we will come back to this problem in chapter 4. In chapter 4, the real question is, what should you set your internal resistance R to? Or excuse me, that one was the different resistance, the one attached to the battery. What should the battery's resistance be set to in order to maximize your total power output? That's a question we'll be able to solve by simplifying this a whole bunch, setting it equal to solve. But since here we're really just focusing on the derivative side, let's skip to this portion. We want to give a practical interpretation to what we just calculated right here. That's also tricky, so let's think of it as a preview problem as well. We can say that this thing, because it's a derivative, it's a form of rate of change. It has units too. The units in the numerator will be the power. The units for the denominator will be the resistance, R, attached to the apparatus, such as the laptop, is what it's referring to there. So we can say that this quantity, this describes the rate of change for the numerator quantity, the total power, for the total power as the thing in the denominator varies. And that was the resistance. As the resistance R varies. So when we say describes the rate of change, when the resistance R varies, we mean the resistance may go up, but we want to say how much power per units of that resistance did it get affected by? Did it go up or down, and by what amount? If we changed R by dropping it, we want to know what is the change of power per unit of resistance as we drop to the resistance, and that kind of thing. Again, a really good analogy here is this is much like a speedometer in miles per hour. Looking at instant you see the speedometer in your car, it's the same kind of interpretation. Well, any questions at all, folks, with this kind of application? Yeah.
Real fast, on the right hand side of the example, you should need to pull down the x on the negative 25.
Oh, negative 25? Yes, I did. It looks like I just dropped that one. Thanks for spotting that. So yeah, that should have been a 20 minus a 25. X coming from that X, absolutely. Other questions at the moment? Okay, well, let's now go to the next section. And congratulations, that's product rule, quotient rule. One thing that we discovered though is we really don't have the full slate of rules even now for differentiating functions. There's some functions we cannot differentiate whatsoever with everything we have at the moment. And that's pretty surprising. That's where the good old chain rule comes into play. The objective of the chain rule is you have a function composition and there's no algebra tricks in the world that's going to undo the fact that you have one function composed of something else. That's okay. The chain rule says there is a process for differentiating that. But to get a feel for how that process looks, I first have an analogy. These are really good, especially since the chain rule is just a weird looking formula. So this gives us some thought of why the formula looks the way it looks. It is silly though, so keep that in mind as we look through this one. It starts by saying a car goes twice as fast as a person on a bike. So by slow car, fast biker. But that whole statement, it's a rate of speed as soon as you say twice as fast. So we can say the rate of change of the car with respect to the bike is 2. 2 being it's going twice as fast. So that's the story so far. And here's the new drama. A person on a bike goes 3 times as fast as a person on foot. So rate of change of person on bike with respect to person on foot is by 3. And here's the overall question. How much faster is the person in the car than the person on foot, given the information above? The question in Leibniz notation would be this. How much faster is the person on car with respect to the person in foot? Any volunteers for what the number should be, just intuitively thinking about it? Kind of confusing in a way, right? If you're not sure, here's a different way to think about it. Notice that the rate of change with car with respect to foot, it's a confusing question because the prior derivatives did not relate the car to the foot at all. But it kind of did in a way. The first one was relating the rate of speed of the car with respect to the bike. The second one was relating the bike to being on foot. And the question is talking about being on foot. These, in fact, are all tied together now in one kind of chain, hence the chain rule. So we can break down this question by saying it should really go like this. So this portion is the question, and you can relate it by thinking of, well, we don't know how the fast the car relates to being on foot, but we can move backwards. We know how fast the bike relates to being on foot. So d bike with d foot would go in. Then we can take this and, well, we know how being on foot relates to being on car from the prior derivative and multiply this way. Rate of change for being on car, divide by rate of change for being on the bike. And there's another analogy going on with this. If you thought in terms of fractions, it looks about right. Now, these are not fractions, so keep that in mind. But if you thought in these terms and you canceled, let me try it a little bit better, and you cancel this way, that's not a bad analogy. You would be recovering the original supposed fraction, d car by foot, in this way, through that cancellation. But that's just an analogy. The reason that's just an analogy is df dx, truly not a fraction, is really the limit as h goes to 0, f at x plus h minus f of x all over h. The reason Leibniz wrote them as a fraction is because he was considering the change in the numerator with the change in the denominator. So it turned into a fraction in his notation. But once you make these connections, you can start making substitutions. Rate of change of bike with respect to foot was 3. Rate of change of the car with respect to the bike was 2. So if you thought to your mind's that sounds like it's going 6 times as fast. You're actually right. It would be equal to 6 altogether. So again, think of this as an analogy. And the most important analogy right here is we use the chain rule to multiply two different derivatives if there's a connection like this, some kind of composition between the functions. Well, any questions, folks, with that initial example one? Okay, so biggest takeaway about the chain rule is you're multiplying different derivatives together. Now, the way they actually go together is not super easy to describe in this kind of format. Turns out prime notation is pretty helpful for this. So here's the whole skinny on the chain rule. We start with g being a differentiable function at x, and then f has to be differentiable at g of x. Reason for that is we're looking at this function composition. This is when the chain rule comes up. So f is equal to f composed of g, and it's defined in this way. Notice there is an inner function there, that's the g of x, and there is an outer function, that's the f. In fact, the easiest way to learn to apply the chain rule is thinking in terms of inner function versus outer function. So we'll begin to do that right here. I want to use green, but that might be a little bit weird. Let's just use arrows on this one. So g of x, I'm going to put a 2 on it and call it inner. I think of it as the inner function because it went inside f when we did the function composition. I'm putting a 2 here because it's the derivative we handled second. Now here f, this is the outer function. We'll put a 1 on it because this is the derivative you handle first. I would call it outer because it's outside in a certain sense. Now suppose you're differentiating this function. Let's track the changes. So if you're doing the derivative of a composition, f of g of x, notice that your inner function gets copied into that location right there. Your inner function gets differentiated there. Let's indicate this is as a 2. 2 is differentiated here. I'll just say for differentiated, that's a long word it turns out. And function 1 gets differentiated in this location. But after it gets differentiated, you plug in the inner function totally unadulterated. It just goes in exactly that way. So that is the chain rule. It's kind of an interesting process. And I have the same kind of caution as before. The most important thing about the chain rule, product rule, and quotient rule is knowing the right time to use it. This time, let's focus on that function. Let's start with the chain rule. And then we'll show how, even though it looks like the same sort of function as spirit, that one doesn't really require the chain rule at all. Well, first things first, if you're going to differentiate this function, you probably want to use the formulas that we have, like power rule and that kind of stuff. So radical notation, although it's pretty, it's not very helpful. Let's rewrite this as x plus 1 to the power of 1/2. Now we're getting started. This is something we can work with. And I'm really looking at 2 elements. There is a square root function that we are writing as a power 1/2, so power 1/2 function. And then there's the x1 plus 1 function. Any volunteers for what function this one would be? Is this the inner or the outer function?
Is that the inner function?
Good call, Andrew. That one is the inner one and this one, absolutely. And sometimes what you can think of as, if you're not sure, the inner function, because we're thinking of a function composition, should be inside of something else. But being able to spot it is the whole strategy for the chain rule. If we can't identify what is inner and what is outer, that entire process breaks down. It'll get all jumbled up. So good eye, we'll call this one here derivative 2, and that one is inner. That means this function, the power 1/2 function, this is the derivative we'll do first when we get the process started. And so we will call this one the outer function. Another way to think about this is, imagine you were doing this as a calculator problem, and you had to put a number 5 in here. Imagine the order operations you would take. You're not going to raise 5 to a power of 1/2. You have to add 1 first. And that's what makes x plus 1 the inner function. It's the first operation that actually has to be done through order of operations. Okay, so really the first thing we do on the chain rule is we analyze the function to decide how it's really composed. And here's the next thing we'll do. I'll do this in 2 lines. First one, I'll just write this y prime to keep it short. We differentiate that one absolutely first. And we're using the power rule to do that. What happens in the power rule? 1/2 will carry down. I don't want to put anything in here right now because I'm just focusing on derivative 1, outer. Right where the red dot is, you'll subtract 1, which means subtracting 2/2, it turns into a negative 1/2. Now, the next thing is more of a pattern that helps out for getting it in just right. Immediately multiply. Recall chain rule is about multiplying by the next derivative. So don't forget the prime symbol. We haven't differentiated this one yet. So the thing we're multiplying by is now the inner function, x plus 1. But in this setup, all you're now doing is taking x plus 1 and writing it in twice. Here's where it gets copied in and it won't be differentiated. It's just done in that spot. When we copy it into this location, we do differentiate it. So this x plus 1 prime location, that's where it's indicating as g prime in the statement of the formula. And that's again what's kind of tough about mathematics. The formula has to be written in this way to indicate the process. But the way you see it, the way you actually work with it on paper feels different. You have to train our eyes to go from here to how you actually calculate in practice down here. Well, we're just about done. One more derivative to go. But any questions first on the setup to that first step? Okay, we're happy with this. Here's the next step. We're just simplifying. I'm not worried if you leave your power as a negative here, so you can leave it in that format. 1/2 can be left just the way it is. So this is 1/2. X plus 1 power negative 1/2. Here, the derivative of x is a 1. That goes to a 0. So we're multiplying by 1. That means it's done right at that stage. We didn't have to do anything further. We've got the right derivative. However, if that was a 3x plus 1, and we forgot the chain rule, we would have forgotten that there's a times 3 right here. And that's how we could potentially lose small questions like on, say, WebAssign and quizzes exams. Watch out for this derivative. Sometimes it doesn't do anything, but if there's a 5x, it would have done something right here for sure. So that's a process with a chain rule. Down on the notes, we'll practice it a whole lot more. But first, we should take a look at this case where I indicated you probably shouldn't use the chain rule. So the thing that's going on with this one is, it's the fact that there's one term in that denominator. Pluses and minuses mess up algebra a lot. You cannot take the square root of the x. You cannot take the square root of 1. Order of operations says you have to add x and 1 first. But you can only do that if you have a value for x. So you're just stuck on this. You must use the chain rule here. However, if there is one term, here's the new thing you can do. This is the same as x cubed to the power of 1/2. And because there's one term here, you can now multiply your exponents together in this configuration. This becomes x to the power of 3 times 1/2, or just 3/2. And this is something we would never use the actual chain rule on. We just use power rule on this kind of stuff each and every time. So we would come down and say y prime is, first 3/2 turns into a coefficient. Subtract 2/2 to drop the power by 1. So x is now to the power 1/2. And you can write this as 3/2 square root of x, but you're fine to leave it just in that format. We're done right at that stage. So just because you see something that looks like a function composition, algebra can unwind that and sidestep the chain rule entirely. It may not save a lot of steps, but sometimes it can save a whole bunch of steps. Well, any questions at all, folks, about these two examples? Okay, what we'll do next is practice a few of these down below to support the homework, get used to the formulas and that kind of stuff. And this first one is more of a get used to what the formula is saying kind of problem. Let's do this one by paring down the actual formula. And give it a try. I guess we can also start color coding these things. I'm going to think of the function that's inner as the green function, and the function that's going to be outer as the blue function. So that's how our color coding would look like. So over here it says f of x is f of g of x. We have another composition. We have several function values here that we have to work through. They tell us evaluate f prime at 0. Probably the first thing you'd want to do on this thing is maybe don't jump to f prime at 0, start with f prime at x. But it's really the same kind of process as before. You think of this one as function 2 because it's inner, f as function 1 because it's the outer function. Then we'll do the same exact process like we did on the notes just above. You differentiate f first, and here's what that looks like. F prime. Then I put in a parentheses as a spaceholder. I immediately went multiply, another set of parentheses as a placeholder, and a derivative. That's the g prime of x I'm thinking of right here when I wrote that in. And right here, I'm thinking of the g of x function over here. So let's take that g of x, it plugs in right here. Recall, completely uncopied, no change. That's the original function, it's not the derivative. But when it goes over here, that one is the derivative. It's really a matter of notation where if you want your prime right here or in front of the function, because we're using the old process, I'll leave it in this kind of format. So that's our step 1. Our second step is, once you have the derivative written out, now we can go to f prime at 0 and do it in a clean way. So f prime of 0 is going to be equal to, well, first it's going to be f prime of g at 0 to start. Then it will be multiplied by g prime at 0 at this location. Here I'll put the prime in the more normal location for this one. Now I can't use any of the f prime values to start this out. We have to do the g of 0 values to begin. G of 0 is here, and then the derivative of 0 is there, the value 4. So now we're just plugging stuff in. So next step we have f prime at g of 0 to begin. So that'll be 8 going into this location through substitution. Then multiplied by g prime of 0 is multiplying by 4. Now that we got to this stage, notice the nasty thing about this problem. There's actual trick right here. The f of 0 equals 3 is totally irrelevant, and the only reason WebAssign would print it is just to see if we use it incorrectly. The one we want is f prime at 8. If we did everything correctly, 8 really should be there. So if we accidentally use the derivative and plugged in a 4, you'll notice, well, there's not enough information to even finish out the problem. That would just mean we got something jumbled up here if that ever happens. So last substitutions, f prime at 8 turns into that -2 we see. So let's throw that in. It's multiplying 4. So the whole thing is a glorified -8 altogether. So again, think of example 2 as its only purpose is for us to look at the chain rule function again, track it through and see how it goes. Just extra practice with the statement of the chain rule. Any questions, folks, on completing that one? Okay, the ones I have next are kind of more honest type chain rule types of questions you'll see in the homework, quizzes, and exams. And here's how they start out. It says calculate the derivative, simplify your answers, and that kind of stuff. And notice the power here is, it seems kind of extreme. There's kind of a reason for that. If it was this, a power 2, it's a legitimate and not a terrible strategy to just expand all that out and differentiate using the power rule, term by term by term. Still a pretty good strategy. But when things get outrageous, power 3, power 4, power 103, suddenly expanding this is not feasible. We're never going to expand this in the remaining time for the whole class. That's just too much work. This is where chain rule is pretty much a mandatory process. So first thing we do is we analyze the situation here. This is a function that seems to go inside something. So that's derivative 2 for inner. And to match up color coding with what we did above, let's also put that in green. This one right here, it's the power 103 function. It's kind of like the function that goes this, x to power 103, except that we took that whole function in green and just threw it inside it. But this part of the function is still alive and well, and we call it the outer function. One, because we have to differentiate that one first. Let's put that in blue, and slight change of heart. Let's actually carry this down as well, just for easy reference. Okay, so now that we have that preliminary work there, here's how the derivative finally goes. Start with f prime of x. That's the derivative of the whole function we're writing in. But now just follow the instructions that we label out. One means we're differentiating this one first, and taking the derivative of that, again, it's like you're taking the derivative of this function on its own. First thing that happens is 103 carries down. The next thing that happens is we're going to put a blank placeholder there because there's something inside, but then the power goes down by 1. It's now to a power of 102. So all that's in blue, since we essentially differentiate this function in spirit. It would be completely the right derivative if we put x here, but we have a function composition, so we'll leave that for the next step. We're throwing in something else, that 8x cubed. So I'll leave that blank just because it's a good idea. Here I'll put in times the derivative. And if you get into this kind of habit, it's really pretty much forcing us to put everything in the right position at this stage. I don't have a chance to differentiate this. I'm just going to copy in 8x cubed plus 9x squared minus 11x plus 6. So nothing changes there. Here we copy it in again, but we'll differentiate it on the next step. So 8x cubed plus 9x squared minus 11x plus 6. So the feature you see right here is no coincidence. This will happen every single time you use the chain rule. And let me see if I can get that to work for me. It's the same thing you see here in the formula. There's a copy of the function in those two positions, but you have to differentiate on the second factor right there. Any questions at all, folks, to that stage? Okay, now when people get really good at the chain rule and you just want to write down an answer, you might write down the answer for this one right away. That's completely okay, but algebraically, it's required to have parentheses as well, because everything to the left must be allowed to distribute into this entire quantity. If you're doing it in stages, it's not as bad because you usually write down the parenthesis either way. It's harder to forget. So copying, I'll have 103, 8x cubed plus 9x squared minus 11x plus 6 to the power of 102. Everything that's in black has just been straight out copied. I'll go back to green since this is now the derivative. But this is like what we were doing in section 3.1. This is the fun and relaxing stuff. Once you see it, we'll go term by term and just write in the answer. Any volunteers from the class, Zoom or in person, for what should go right here?
$24x squared.
Awesome. Anyone have the rest? Or anyone for the next part? Awesome, we've got an 18x next. And then last position, or last term. Yep, absolutely. Minus 11. Close the parenthesis, and we did it, folks. That's the chain rule on a strange pi-degree polynomial. There's nothing further to do here. You can't distribute 103 in. Order of operations with the exponent prevents it. And there's no value in expanding this kind of stuff out either. Usually we just leave it in its factored form after differentiating. Well, we did it. That's our first honest, this is what an exam quiz homework question would look like, chain rule problem. Any questions at all? Let's try out to a couple more just for the sake of practice. Here's where things get a little bit weirder. Sometimes we'll see problems that they just don't seem to fit into any right category, like this one here. It's not a quotient rule because it's just a constant in the numerator. There's no x's. It's not a product rule of any kind, really. This one turns out to be a function where you need to fix the formatting, and then the rule you use kind of reveals itself. How are we going to fix the formatting? Well, my first complaint is that's radical notation. For derivatives, we very much prefer exponential notation. So our first step, we're going to say f of x is now 9 divided by, it's indicating a fifth root, so we're going to write that as power 1/5. Then inside is 2x squared minus x. At this stage, this is still not good enough. Our formulas for differentiating don't work well for stuff like that in the denominator. We want our formula to work more like this, where the power is relative to a base in the numerator. So we need to switch positions on that thing. That makes the exponent a negative. So it goes 9, 2x squared minus x to the power of negative 1/2. In this format, suddenly everything is a lot more clear. We're going to be using a power rule here. We're going to be using power rules here. That's also definitely a chain rule. This is the inner function. And the power negative 1/5 function, that one is outer. We're also using the constant multiple rule. Notice that there's nothing happening to the 9 because it's multiplying right here. Well, that's the format. Let's give it a try next. Any questions with the preliminary analysis on this one? Okay, so let's give this a try. F prime of x is going to be equal to, first thing that happens is this power right here, negative 1/5, is going to come down and multiply the 9. I'll write this out in a couple steps. So here's 9 to start, multiplied by negative 1/5. Give it a nice blank spot right there for the placeholder. Now subtract 1 from this, which means subtract by 5/5. We get to negative 6/5 altogether. Next step, this is more for safety, for getting through a pattern on getting it right. Immediately convert to multiply by, and I'll change the color coding, by something. So this is our first step in the chain rule process. When it says 1 outer, here it is. We took the derivative of the outer function, derivative number 1. When it says 2 inner, you copy it in here, no changes. And right in this location, we still have to differentiate it. So that's our last one to take on. And actually, we're pretty much done then, right? That's a nice fast derivative from chapter 1. So the whole result turns into, from here, negative 9/5. Then a little bit more copying, 2x squared minus x to the power negative 6/5. And for this one, just don't forget it still requires parentheses because we're going to pick up 2 terms. It'll turn into 4x minus 1. And we did it, folks. This is where it starts to get a little bit nastier in the homework. When you see weird things like this, really the objective is algebraically, just contortionistically maneuver it so it's something more familiar, and then you'll be on your way. Well, part B is getting a little bit trickier so far. Any questions so far before we go to the next? Okay, so here's a new chain rule problem here down below. But this one's also kind of a reminder in a certain sense. We had a lot of rules in the last section, 3.4, with the quotient rule, product rule being added to it. But now if you add chain rule, the chain rule can go together with everything else. It's possible to write down a problem that uses every single differentiation formula, rule, or process that we've discussed in the whole course. And this is one of them. Notice that there's a product, so it's for sure the product rule. And the powers here are really pretty high. So we're not going to expand these out. We'd be here all night. We're going to take care of these as chain rule derivatives. then bring them back together with the product rule process all at the same time. So this is where they start to get a little bit nastier. These are the harder end problems in the WebAssign, I'd say. They start to become not good exam questions. When you see these harder ones in WebAssign, think of them as they're really great practice for the exam, but you're really doing like 3 different problems rolled into one. Same with part D as well, but let's hide that one for the moment. So starting off with this one, let me put down just a sequence of thoughts. First, setup, product rule. It's really the first thing going on with it that's a problem for us. So we'll say G prime of V is going to be equal to, instead of putting down the placeholders like we did before, I'm going to start writing it down like this. Derivative of the first function with a bracket, 2v squared minus 7 to power 4, and here's the prime. And what do we do next? We just copy in the second function. Still needs a parenthesis, v cubed plus 5v minus 1 to power 8. Next, there's always a plus in product rule. Plus in product just kind of makes sense. We're copying this one this time. So 2v squared minus 7 power 4. And we're differentiating that one. So I'll put in a bracket to show it better. So bracket v cubed plus 5v minus 1. Forgot a parenthesis inside there to power 8. Close the bracket and put a prime symbol on it. So we're following the process as indicated. There's a derivative on the left, derivative on the right with a plus in the middle. But then when you look at each of these derivatives, they are honest problems in their own right. This is like a 3-problem kind of part C right here all of a sudden. So we'll use the idea of we're going to just break them up and handle them individually. Let's maybe go purple for this one, blue for this one, and let's do 2 chain rules at once and see how they go. So let me call this, say, a y equals. Oh, that's the wrong color. Let me try again. This one will be a y equals 2v squared minus 7 to power 4. So down below, I'll call this one a y prime. First thing that happens is this power 4 is an outer function by the patterns we've seen in the prior problems. The 4 should come down. Put in a big open parenthesis, and power 3 is the next value. They'll multiply by something with a prime inside. Next thing we do is just copy in everything you see there exactly. So 2v squared minus 7 here and here. Now this one's almost done. We have this is equal to 4, 2v squared minus 7 cubed. Now here, the only thing that happens is this 2 will hit this 2, giving us a 4v. That one's a constant, so just 4v on that derivative. Now, because we have to bring and put all this back together, on these steps in the middle, it's a good idea to simplify them as much as possible. Let's call this one 16v times 2v squared minus 7 to the 3rd power. So that's taking care of the chain rule on this one. We'll plug the result right back in here when we go to the next step for G prime of V. Then, that was so fun, we're just going to redo it in the same exact way right over here to the left. I'll call this one y equals v cubed plus 5v minus 1 to the 8th power. So if you're differentiating this one, y prime will be power of 8 coming down. New power is 7. We'll multiply by some derivative and copy this thing into the remaining positions. V cubed plus 5v minus 1 here. V cubed minus 5v minus, plus 5v minus 1 goes here. Kind of weird to miscopy that close together on steps. Last thing to do is handle this derivative. But that derivative comes with 2 different terms, so we'll still need parentheses around that one. Y prime is now equal to 8 times v cubed plus 5v minus 1 to the 7th power. Now here's our new step. Derivative of this will turn into 3v squared plus 5. So we are now ready to make a substitution here and here for those quantities just calculated. Any questions or comments so far, folks? Okay, so first we set up the product rule. We can say next. Work the chain rules. Now you can obviously do this all in one single line. If you're comfortable doing that, I think that's a pretty cool way to solve this one as well. But I think for problems where so much is going on, dividing it up and doing these each separately, that might be the better strategy for you. You could try different ways of doing it. But if you did work separate chain rules, then you can now say, here's our next step. Finally, return to G prime of V. We're going to make two big substitutions, and here's how it looks. G prime of V is going to be equal to, in this position, it's 16V. 2V squared minus 7 to the 3rd power. Put a little bracket on that to show we made a substitution there. Then the rest of this copying, let me zoom out a touch. That's going to be more helpful than scrolling, I think, at this point. It's V cubed plus 5V minus 1 to the 8th power. Then plus 2V squared minus 7 to the 4th power. Over here in this position, we'll make another substitution. Everything there in the green, blue, black brackets turned into this quantity, 8. And let me get my parentheses a little bit better set up. I want to put my 8 in front and then the parentheses. I think that's the better way to write it in. Then go parenthesis V cubed plus 5V minus 1 to the 7th power, multiplying by 3V squared plus 5. So that's where all that went. Let me indicate it came from that location. We got it, folks. That's our full-on derivative. If this was a real problem on a quiz, an exam, I'd be okay if you stopped at this point. But the challenge with these kinds of problems is it's not really simplified. WebAssign can complain about these sometimes. So from here on out, we're going to do algebra to simplify this as much as possible. And there's actually a lot of value to that, because in chapter 4, we want to optimize. And the best way to optimize is we're looking for when the slope of the tangent line goes like this, when it turns horizontal for a 0 slope. And the best way to find those is by solving G prime of V equals 0. But the only way we're solving that equation is if you simplify this as much as feasibly possible. So let's make that actually happen. I wrote all that out just because sometimes it's good to know why we're working really hard when it's now just pure algebra. That's the reason. It's coming back in chapter 4. And here's how it simplifies. We're looking for the greatest common factor to start. Notice that between the constants, 16 and 8, you can divide out an 8, so that begins the process. There's a lonely factor of V. There's no single factor of V anywhere, so that one cannot factor out. But now let's focus on this region. 2V squared by 7 to the power 3, 2V squared by 7 to the power 4. It appears twice, so it does in fact factor out. 2V squared minus 7. What we have to get right is the actual power. What is the highest power we can factor out? Anyone recall? It turns out it wouldn't be a 4, it'd be the 3. To me, that's what's weird about factoring. We want to try to divide out something from both terms, which means we have to actually pick the smallest power between them. And notice how weird that sounds. With greatest common factor, you pick the minimum power between the like factors. It just sounds weird. But it's what we must do. Math is just weird on its own sometimes, and we'll live with it. Let's move on to the next thing. V cubed plus 5V minus 1 does occur again right here. But we only can take out the minimum power, the 1 to the power 7. So let's write this in as v cubed plus 5v minus 1 to the 7th power. Beyond that, the only other factor we haven't really looked at is this one. But 3v squared plus 5 doesn't show up anywhere. So much like that v that's just kind of alone, this one's going to stay right where it is as well. So that to the left is the greatest common factor. Factoring out the greatest common factor is a type of division. What we're going to do is take this 8, divide it here to the 16. We'll have a 2 left and a v left. But the v squared by 7 to power 3 totally wipes this out. This is now just gone. When we go to v cubed plus 5v minus 1, it cancels off all the factors except 1. It just leaves behind v cubed plus 5v minus 1. So literally, think of it like this. There's a big fraction bar, and you're dividing out in this way, writing down the survivors, and that is the right thought when you're factoring out a greatest common factor. Any questions so far, folks, with that first result? Okay, next thing we'll do is, well, do that same process again. We're moving across addition, so we just write it in. And now we're looking at everything right here. Everything highlighted temporarily in yellow is going to be divided by the greatest common factor to the left. First, 8 and 8, they cancel off. We don't have to write that in. Next, 2v squared minus 7 to power 3 cancels into this one, but it drops it to a power 1. It leaves behind 2v squared minus 7. So we just write it in that way. Next cancellation is this whole thing completely cancels that whole thing. We don't have to write in anything for that because the powers are the same. But what it did leave behind was that one right there. Had nothing to cancel into it, so we just copy it down. 3v squared plus 5. Close the parenthesis. If you're a bracket person, close the bracket, or a larger parenthesis if you put a larger parenthesis. And we factored it a little bit. Now, everything on the left here, it's completely all settled. But now the downside is, because we factored a little bit, everything inside here can now simplify, and it in fact does. So we're going to now crank out distributing 2v through and FOIL this out to combine our like terms next. So let me write in. First, it's a bunch of copying. 8, 2v squared minus 7, power 3. v cubed plus 5v minus 1 to power 7. I'll convert this to a large parenthesis where it was a bracket. And now start distributions. We'll get 2v power 4 plus 10v squared minus 2v. This one's going to be a FOIL, so I'll bust out the arrows for this one. Let me know if anything gets put down incorrectly. This one will be a plus 6 v to the power 4. Here to here is plus 10v squared. Next, let's distribute the negative 7 through. That'll be negative 21v squared. And here to here will be negative 35, provided I did every operation correctly, copied them down correctly. Let me know how they did. Does that look all right to folks? Okay. For these longer problems, the more time you spend just double checking your work on a step-by-step basis, the faster you finish the web assignment problem. That's a sad reality about math, but it pays to go slow. Sometimes you're actually going faster. So next step, I'm not worried about anything here. We're just going to copy them in. 8, 2v squared minus 7, power 3. v cubed plus 5v minus 1 to power 7. But at this stage, we should be able to finish the problem. We have v power 4 to start. Let me use some kind of coding symbols here just to help my eyes alone. It's easy to drop a term here. Looks like 8v power 4 altogether. Now, we don't have anything to power 3, but from here, we have 20v squared minus 21v squared, so negative v squared. Enough dust is settled. I feel confident to just identify the rest. Looks like minus a 2v. Far out here is minus a 35. And finally, this is the stopping point for us. There might be a way to factor something inside here, but if it's a fourth degree polynomial, I would say definitely leave it alone. You don't have to bust out any polynomial theory looking for zeros and factorizations. It's just fine at that stage. Well, we did it, folks. This is when the derivatives start to get a little bit nastier. The takeaway for this problem is it's just good to know when a product rule is even being identified, and then when it conflates with a chain rule as well. But any problem like this is really considered 3 different problems on a real exam. I would actually break it up so you don't have to do that much on any one problem. Well, we did it, folks. That's the full process. Any questions or comments about it? Okay, when we turn on Wednesday's class, we'll try this again with a quotient rule type of problem together with the chain rule. From then on out, we'll take a look at some interesting formulations for chain rule whenever we're dealing with exponential functions again. I think this will be a good stopping point for us. These problems are getting longer than 4 minutes at a time. So we'll reconvene Wednesday on the next example. Have a great night, folks, and I'll see you all on Wednesday. There you go. You bet.
Have an excellent day.
Thanks, you too.